Hello, my name is Alejandro Almeida, and I'll be presenting the following paper titled Side Channel Driven Intrusion Detection System for Mission Critical Unmanned Aerial Vehicles. This paper was submitted to International Symposium on Quality Electronic Design of 2024. I am going to be the major presenter. The other authors that contributed to this paper are Muniba Asif, Dr. Mohammed Tahidir Rahman, and Dr. Mohammed Ashakir Rahman. So just a little bit more about me. I am a PhD student in electrical and computer engineering at Florida International University. I conduct research on behalf of the Analytics of Cyber Defense Laboratory. My research topics include side channel defense applications on hardware, embedded systems, security of autonomous vehicles, and machine learning applications in cyber defense. Aside from my studies, I am also volunteering at the Anti-Human Trafficking Initiative, Team ATII, where I offer my knowledge and skills to conduct digital forensics. Due to the ease of use and the high availability of small-scale unmanned aerial vehicles, there's been much attention regarding to it in the public eye. UAVs have a wide range of applicability in both military and civilian sectors. It is also known that in the combat against terrorism, speed and efficiency are of the most vital essence, and this can be significantly augmented by the use of UAVs. They are also a valuable asset when it comes to search and rescue missions, as they are able to access locations that would otherwise be difficult for an individual to access. Although there's a lot of positive things that can be accomplished using UAVs, they're still susceptible to cyber attacks. Particularly, this paper focuses on hardware Trojan effects and how they are considered one of the most malicious and biggest concerns when it comes to um, the usage of unmanned aerial vehicles. So a hardware Trojan is a malicious modification that's basically made to an authentic design to cause malfunction, steal, or leak sensitive data. Hardware Trojans can cause denial of service attacks or impede the normal functioning of the device or disrupt the device completely. The vulnerable computing devices are not limited to CPUs, but also to ASICs, FPGAs, and others. Due to the intensifying cost of circuit fabrication plants and the overheads, um, a lot of these circuits for these devices are actually manufactured offshore, where the security cannot be guaranteed or verified. So there is a much higher risk of having hardware Trojans implemented. So this study aims to develop a side channel based intrusion detection system against hardware Trojans on mission critical UAVs. And the hardware Trojan would basically selectively alter the PWM signal, which would lead to other ramifications and consequences. The main contributions of this study are as follows. Uh, we determined a feasible side channel that can be used to construct an effective IDS, and we demonstrated how changes in the impedance levels could lead to the discovery of a hardware Trojan. We also demonstrated how machine learning classification tools can detect hardware Trojans on UAVs, and we showed how our proposed method can be more optimal and effective than other hardware Trojan detection systems that are currently out. So a little backend on the working principle of UAVs. So UAVs contain several components that allow them to function as intended by the manufacturers. You can see here on this image, this is a UAV without the propellers. One of the most critical components is the flight controller. The flight controller basically ensures that the PWM signals are delivered to the appropriate motors. In this case, we used a quadcopter UAV, so it had 4 motors for each of the propellers. The flight controller also have other functions such as coordinating sensors and power systems. So a little bit of background when it comes to side channel analysis. So side channel analysis focuses on the operational characteristics and properties of a system such as, for example, power consumption, EM radiation, timing patterns, sound. In this example, you could see you have a computer, and in the computer there is a smart card reader attached to it through, like, let's say a USB port. Let's say a malicious threat actor wants to gain information from the smart card, basically steal the numbers on it or the expiration date, everything. They would pretty much be able to do this using an oscilloscope with an electromagnetic probe. Whenever the smart card is being read by the smart card reader, the electromagnetic probe will pick up the EM radiation that's being emitted, and using the signals from the EM radiation, a threat actor can actually figure out information regarding the card that was used. There are some related works regarding side channel techniques for hardware Trojan detection. Some example are post-silicon power mapping on residual thermal maps. Um, in this example here, they basically had 2 ships. We had a testing ship and we had a golden ship. The golden ship is the ship that we know for a fact does not contain the hardware Trojan. The first step is images acquisition, so we would use some type of device to gather thermal maps from the ships while they're in operation. We would then perform data processing on the thermal images using pre-processing and difference filtering. We would basically get the difference, and then we would perform our analysis based on those differences. Another example of a side channel technique for hardware Trojan detection that's been published is detection through backscattering side channel. So the way this would work is we would have an RFID reader that consists of a transmitter and a receiver. The transmitter would send a continuous wave over to the RFID tag on the device. In this case, it would be on the ship. And then we would get a modulated signal back to the receiver on the RFID reader. And based on the results that we get from this backscattering technique, we are able to discern if there's a hardware Trojan or not. So as previously mentioned, machine learning can be used in order to detect anomalies. So some examples are the autoencoder based anomaly detection. This is based off LSTM. And classification such as random forest or XGBoost. In here you can see some examples of how it works. On the picture on the right you see a random forest. So basically, just an example, we have a basket of fruits and we want to know which fruit was picked from the basket. We would put in like several inputs through each of these branches into trees, and then based on majority vote, we could predict which fruit was actually picked from the basket based on different functions within each of these trees. So attack model, so this section illustrates the threat model that is used for conducting our test. Our threat model consists of a hardware Trojan that's capable of inverting the PWM signals on UAVs, along with a description of how the attacks are carried out. So, as we know, hardware Trojans are increasingly becoming a significant threat that risks the security of modern integrated circuits in the industry. An adversary can intentionally modify the IC design to cause operational failure, denial of service, or leakage of valuable information. To facilitate research work in this area, a better understanding of what various types of hardware Trojans and could look like on the integrated circuit design could be essential because it will provide us with much more versatility, and we could come up hopefully one day with a general solution for this issue. So the framework consists of the following assumptions. The first assumption is that the attacker has complete knowledge of flight controllers, FPGA, IC, and HT design, meaning they're well versed in these topics. The second assumption is that we assume that the hardware Trojan can be implemented at any phase within the supply chain, and that the hardware Trojan can go undetected and into the market. And our third assumption is that we consider the attacker to have access to the appropriate tools and components necessary to design the hardware Trojan. So looking more into the hardware Trojan is composed of a trigger and a payload circuit. A good design of the trigger and payload circuit is crucial for the study's effectiveness as it controls the hardware Trojan's behavior and activation frequency, and also allows us to determine whether our intrusion detection system can detect stealthy designs. So differences between the trigger and the payload circuit, we have here an example. So a trigger circuit is basically a circuit that activates the payload when a certain condition is met. If you look on the graph down below, the first one on the left, we have an input coming in, and the input goes into original circuit, but if there's a hardware Trojan implemented, it would also go into the trigger circuit of the hardware Trojan. If the certain conditions are met on the logic within the trigger circuit, it would release the payload. The payload could be some kind of logic that would essentially disrupt or change the behavior of the circuit. And you can see here on the right, this is another example. So we have a simple combinational circuit, and then we have on part B a Trojan with the trigger and payload added to the original circuit. So the trigger in this case would just be an AND gate, and the payload would be this XOR gate that's added here. And basically whenever this trigger would be activated, it would send a value of 1 to this XOR gate, and it would change the output of the circuit. So this is our attack goal. So we have the drone while it's in flight, and we have our hardware Trojan, and the hardware Trojan is going to check whether or not the signal for the main controller unit, in this case it would be the flight controller, to the rotors would be 1011. If it is, then we would invert the output signals and have a multiplexer flip the values. If not, we would just continue normal operation. As part of our hardware Trojan implementation, we used some integrated circuits in order to accomplish our design of the hardware Trojan. In this case, we used one dual 4-input AND gate, two of the single 8-channel analog multiplexers, and one CMOS NAND gate. As you can see here, we have our hardware Trojan implementation on the circuit level. We have the 4 inputs, which are the 4 PWM signals. In this case, it's A, B, C, and D. And we have our payload circuit, which consists of all these blue elements. And you can see here we have 4 NAND gates, 1 AND gate, and 4 multiplexers for each of the inputs. So basically, whenever a signal of 1011 is sent through, it would actually flip the values for the multiplexers. So it would disrupt the operation of the UAV while it's in flight. As part of our validation, we wanted to make sure that our hardware Trojan was stealthy. In order to do so, we need to measure the hardware Trojan activation frequency. The way we did this is we basically had our unmanned aerial vehicle set up with the hardware Trojan, but we set an Arduino to capture um, whenever the trigger circuit is activated and increment a value within the Arduino code by 1 each time the trigger circuit is active. And we would see the results of this on an LCD display that's connected to the Arduino. So we tested this for different time frames. Um, we tested it for the 10-minute and the 1 hour, and then we repeated it again for 1 hour just to make sure that the values are correct. So for 10 minutes, there was a total number of 2,251 cycles, and there was 78 times in which the hardware Trojan was activated within those cycles. If you get the activation rate, it's basically 3.46% of the time. For the 1 hour, we had the hardware Trojan activating 451 times out of 7,237 cycles. That is a 6.23% activation rate. After repeating the 1 hour again, we got a 4.19% activation rate. This is what we originally aimed for because we wanted it to activate 1/16th of a time. So as long as it's below a 6.25%, we should be good to go. We performed some experiments using JMapSim. It's basically a simulation tool that is able to gather information from the flight controller and the UAV while it's being in operation. It provides hardware in the loop and software in the loop simulation options. And what we observed from the logs using a hardware in the loop simulation and having the hardware Trojan being implemented on the UAV is that there's some erratic changes when it comes to the thrust of the device. And these thrusts pretty much align with the time of the hardware Trojan being activated. So another experiment is we basically demonstrated that the combination of impedance, resistance, and reactance is a good input for our intrusion detection system model. And this was done by comparing the different physical parameters of the device under test, which we were also gathered by the vector network analyzer that we used, which I'll talk more about it in a bit. So some of these parameters are resistance, phase, reactance, and power consumption. So as you can see here, there's some changes when it comes to the impedance, resistance, and reactance of the device when there is a hardware Trojan and when there is not. You could clearly see that without the hardware Trojan, it has some spikes on the data, but it's not as much as with the hardware Trojan. The hardware Trojan kind of impedes the normal operation. It does not allow um, the parameters to reach the values that they're actually supposed to be reaching. So this could definitely lead to some disruption on the way the drone operates and could cause it to crash as well. So we gathered this data, these three parameters using a vector network analyzer. And as you can see here, using the vector network analyzer, we were able to construct a Smith chart. And the Smith chart is able to plot the impedance values at different frequencies over time. So without the hardware Trojan being the golden model, we could see that everything is kind of like smoothed out, the values, compared to the results that we got with the hardware Trojan. With the hardware Trojan, there's a lot of more spikes and variations when it comes to the impedance. So our defense model proposal is an application of a neural network with XGBoost to effectively detect hardware Trojan in UAVs based on the results gathered by the experiments in our case study and our evaluation. The best XGBoost inputs are three parameters: impedance, resistance, and reactance. So how did we do this? Well, this flowchart basically illustrates the process flow of our IDS. We have the UAV with the hardware Trojan. We use the vector network analyzer to gather the data. In this case, it would be impedance, resistance, and reactance. Using that data, we would train the model, and we would train it with XGBoost classification. And then we would evaluate the classification predictions. And based on these predictions, we could tell if there's a hardware Trojan or not present on the current device. As part of our evaluation, we have the proposed research questions. So our first research question is, can the IDS detect the presence of hardware Trojans of varying activation frequencies? So instead of 1/16 of a time, maybe 1/32 of a time or 1/48 of a time. Our second research question is, how effectively is our IDS detecting different hardware Trojans? Third question is, do different parameter variations improve results? Fourth is, how effective is the side channel based defense technique in detecting the hardware Trojan at different thresholds for the machine learning module? Our fifth research question is, what is the computational load? Our sixth research question is, how feasible is it to implement the IDS model? And lastly, our final question is, how do different classification modules perform and which one is the most optimal? So as you can see on the graph here, we have our IDS performance with varying hardware Trojan activation frequencies. This is to answer the first research question. And we could see a performance versus trigger frequency graph here. We have different metrics. In this case, the metrics that we used is accuracy, F1 score, and ROC. As you can see, over time, the more, well, in this case, the less the hardware Trojan is being activated, we have decrease in the accuracy, F1 score, and ROC. But even at 1/48th of a time in which it's activated, it's still within a pretty acceptable range. I would say is around 0.84%. So the accuracy is pretty good when it comes to very low activation frequency. The F1 score is a little bit more accurate. It's a little bit higher, as well as the ROC. The ROC does good. There's a good ROC value at 1/48th of a time. Obviously, the more frequent the hardware Trojan is activated, the better the metrics results are. In this case, even the RLC at 1/4 of a time is almost at 100. So it's really good. It's not bad. It's definitely acceptable at different trigger activation frequencies. So our second question is, what is our IDS performance with different hardware Trojan payloads? In this case, we use the same setup, except the payload circuit now, instead of inverting the signals, it would actually communicate with another like embedded device, in this case like an Arduino Uno, to send data containing the information on the device. In this case, it could be like sensor data like orientation, altitude, the distance it has traveled, its velocity, everything over to a remote server. This is done using Node-RED, and we would basically forward that data over to an SQL database. And as you can see, we have the RLC AUC score on the information leakage hardware Trojan. We basically we tested the output of our performance using the IDS, and we could see that it performed very well. It had a good true positive rate ROC curve. The ROC curve is 0.97, which is very good. For our third question, we have the performance with varying feature combinations. So we tried the different parameters that we gathered using the vector network analyzer, and we input them into the machine learning module to try to see which ones provided the highest accuracy F1 score and ROC scores. As you could see, when we only have, for example, the impedance, it's not as high as compared to when we have the impedance and the resistance being considered as well. The one that provided the most positive results in terms of accuracy and the other metrics is when we had a combination of all three parameters as the input values for our machine learning module. In this case, when we had all three, the impedance, resistance, and reactance, is when we actually got the best results. So we wanted to evaluate the performance using varying thresholds. In this case, we did it by comparing the results using an SVM and an XGB classification. As you can see on our metric values, we measured accuracy, precision, recall, and F1 score. Let's just say that XGB performed the best. The top one is the SVM. SVM, as you can see, it had a pretty bad F1 score, pretty bad precision, and a bad recall, although it had good accuracy. But the XGBoost really stood out because all four of its values, the accuracy, the precision, recall, and F1 score, were within acceptable ranges at different thresholds. So this is one of the decisions why we chose XGBoost as our classification module. For our fifth research question, we wanted to know the computational load and ease of implementation of our IDS proposal. We were able to basically see the process time in milliseconds using Python's time library. On average, it would take around 86 milliseconds for the whole machine learning classification to finish training and giving the output. And it would only occupy around 197 megabytes of memory. Due to these results, it is safe to assume that this IDS implementation method is feasible as the modern computational power exceeds 197 megabytes of memory. It's much more actually nowadays. We're talking about gigs and gigs. So it's pretty good. It's easy to implement and it doesn't have that much of a heavy computational load. For our sixth evaluation question, we wanted to evaluate the performance of different classification modules and kind of like compare their metrics based on how accurate they're able to actually detect a hardware Trojan on the ships. We used random forest, linear regression, k-nearest neighbors, SVM, and XGBoost, and we compared the results using the following metrics, which is accuracy, F1 score, and ROC. You can see the ROC curve for the different models. In this case, XGBoost had an ROC AUC of 0.995, which is super good. Second place would basically go to k-nearest neighbors, and third would be random forest. XGBoost provided the best results throughout all of these metrics in terms of accuracy of one score and ROC, and that is the reason why we decided to go with XGBoost instead of, for example, random forest or k-nearest neighbors. When it comes to future works, we would like to demonstrate the possibility of an IDS technique that does not depend on machine learning. We could also benefit from a node insertion analysis. This would basically allow us to study the impact that hardware Trojans could have depending on its location of implementation. In conclusion, this paper demonstrates the importance of having effective countermeasures when it comes to ensuring mission critical UAVs, especially since they're heavily used in the military and civilian sectors when it comes to like fighting terrorism or search and rescue missions. We basically introduced hardware Trojans and their implications in UAVs. Using different experiments, we determined the side channel that we could construct our IDS around in order to detect hardware Trojans. We defined our problem and attack module by creating our testbed hardware Trojan and inserting it into a UAV. Our defense proposal consists of an XG boost classifier that takes in three side channel parameters. In this case, it's the impedance, resistance, and reactance. And this allowed us to detect presence of the hardware Trojan. Our results ultimately demonstrated that by using machine learning, we can efficiently detect hardware Trojans on UAVs. So for some acknowledgements, we would like to give thanks to these two agencies that basically supported our research. The first one is the National Security Agency. We have the award number here, and the second one would be the Department of Energy. Thank you to both of these agencies for helping us make this study possible.